10.8 notes, vectors, page 3. So example 5, let's take a look at what we got here. We want to show that the vector v with the initial point at 2, -3 and terminal point at 5, 1 is equal to vector u that has an initial point at 6, -1 and terminal point at 9, 3. We want to draw the position vector on the same grid as both of these and then find the magnitude and direction of each vector. So let's start with what we're asked for. Vector v has got an initial point at 2, -3, terminal point at 5, 1, so there's my vector v. We have got vector u with an initial point at 6, -1, terminal point at 9, 3. Here's my vector u. And so the position vector has got to go over 1, 2, 3, up 1, 2, 3, 4. Make sure this one did the same. 1, 2, 3. Yep. Up 1, 2, 3, 4. So geometrically, I can show that these two are equal. I mean, basically, they're two congruent triangles, if I look at it this way. So for my position vector, we're going to start at 0, 0. We know we go over 3, up 1, 2, 3, 4. Here's my position vector. It's the vector 3, 4. And so we are going to make sure that u and v actually match up with that. So here's vector v. I have got, let's see, terminal point 5 minus initial point 2. And for y, terminal point 1 minus initial point -3. I get the vector 5 minus 2 is 3. 1 minus -3 is 4. Okay. My direction we want to make sure we crank that out. Again, double check really quick. Make sure your calculator is set to degrees. And we get 53.13 degrees. It's going in the positive direction. Makes sense. Our vectors are going up to the right. So let's see what happens here for vector u. Well, I guess I never figured out the magnitude of vector v. I guess I should do that. Magnitude of vector v is the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16. Square root of 25 is 5. Okay, so we got that all in there. I did cram that in. We're going to move our u down just a little bit. So for vector u, we have terminal point minus initial point, 9 minus 6. We have 3 minus -1. We've got the vector 3, 4. Absolutely no reason to think that the inverse tangent of 4 over 3 is going to be any different than what we found a minute ago. As soon as we find that the components are the same, we know everything else is going to be the same. Okay. Two vectors are equal if their magnitudes are equal and their direction is the same. So we can say v is equal to u because The magnitudes are the same, and the directions are the same. Okay, so that's how we know if two vectors are equal. Let me write that up here. Okay. We like writing these in component form. It makes certain operations super easy. So on to part 3, perform vector addition and scalar multiplication. So to find the component form of the sum of two vectors, and you guys, I found this graphic online. You've got the link there if you'd like to go and see a little more about vector addition, subtraction, scalar multiplication. It just had nice diagrams about what's going on here. So we've got two methods that we're going to talk about when we talk about vector addition. And if we look at them graphically, we've got something called the head to tail method, which means if I'm adding two vectors, I would travel along one vector, and what I got to the end, I would go ahead and travel along the other vector. Keep in mind, doesn't matter where vectors are placed, they still have that same magnitude and direction. Okay. Component-wise, we've got that over here to the right, kind of nice. When I'm traveling along one and then the other, I'm just going to add my two x components together. I'm going to add my two y components together, and I get the sum of two vectors as the vector of the sum of the components. Okay. Since subtraction is just the same as adding the opposite, we're going to find that it works the same way for subtraction. We'll talk a little bit about scalar multiplication later. A scalar is just a number that we're multiplying by a vector. Notice here, down on this part, it just means that that scalar is multiplied into both pieces. Okay, so everything here is pretty straightforward. Here's what we're going to do. We are going to go ahead and do this both ways. We are going to add these component-wise, and we are going to add these graphically to show how those tie together. So here is my vector u. 3, negative 2, so over 3, down 2. Here's u. And we've got vector v, negative 1, 4. I am adding these together, so I'm going to put my initial point right at the end of this. I'm going to go back 1, up 1, 2, 3, 4. And here's my vector v. Notice I'm using the head to tail method. I kind of like that a little better than parallelogram, but feel free to use whatever you would like. If I want to add vector u and v, I'm going to add the x components. 3 plus negative 1, I'm going to add the y components, negative 2 plus 4. And I get 3 minus 1 is 2, negative 2 plus 4 is 2. I get the vector 2, 2. If I take a look at my graphical here, 2, 2 starts at 0, ends at 2, 2. So you can see how both graphically and component-wise this works. We get the same thing. Okay, let's take a look at what happens when we subtract these. And I'm going to go ahead for this one. I'm going to do the actual subtraction first, and then I'm going to graph it and show you how I'm thinking about this. So I got u minus v. Component-wise, 3 minus negative 2. Sorry, not minus negative 2. 3 minus negative 1. Sometimes you say something, you know it's not right, but you can't stop yourself. And we're going to back way up and do that again. There's nothing wrong, just bothered me. So we're going to subtract the x components, 3 minus -1. We're going to subtract the y components, -2 minus 4. Okay, now keep in mind what this is. This is 3 plus the opposite of -1, and -2 plus the opposite of 4. And I'm just writing it that way because that helps it make a little more sense of what we're doing when we subtract. Okay, so here's how I'm going to do this. I'm thinking of this as, where can I write this? U minus V, come on, as U plus -V, which means my V is just going the opposite way. So my U again, 1, 2, 3, -2. My -V, instead of being -1, 4, so V is -1, 4. Think about how I used it in this subtraction. -V was a +1, -4. And so that's what I'm adding to this tail. +1, negative, so from the tail of U, I got 1, down 1, 2, 3, 4. -V. So I'm adding actually U plus -V. I get that resultant vector that is over 1, 2, 3, 4, down 1, 2, 3, 4, 5, 6. So whether we do this algebraically or geometrically, we end up in that same place. Here's that vector for -6. I like the graphical because sometimes it helps me make sense of what's going on with the numbers.